All right, let's start then for a day. I see some 12 students here. All right, so did you all go through week 11?
Yes, ma'am. Halfway.
Okay, yeah, so week 11 has many topics. Okay, so what about others? Did anyone else go through it?
Yes, ma'am.
Okay, so any specific doubt that you have from week 11? All right, okay, we'll start. So in week 10, we had stopped at soft margin SVM. Like we had completed hard margin SVM and then we had moved to soft margin SVM. So I will start from here. So we had seen the formulation for the problem in case of soft margin SVM, and the formulation, the primal problem uh, that we had seen was minimize over W epsilon half of norm of W square plus C times sum over epsilon I varying from 1 to n, where C is greater than equal to 0, subject to the constraint that W transpose xi yi plus epsilon I is greater than equal to 1 for every I and for epsilon greater than equal to 0 for all I, right? So this was a formulation that we had seen in the last week, right? So in soft margin SVM, if you remember, like we were not just looking for the weights that linearly separated my data set. We were allowing every W possible, every W that is feasible, any W we choose, and we are saying this is a good candidate for my W. And now, if you choose any W, what was happening is if I choose any W, there will be some misclassification. There will be some points which are correctly classified, some points which are not correctly classified. So what we had said also, whichever point is not correctly classified, let just that point can pay some bribe and they can move to the correct side, right? And from there we had come to this formulation of the soft margin SVM, and we had seen that so C is basically my hyperparameter. Okay, so C is hyperparameter for us. So what we had seen is if I take C to be 0, okay. So if I take C to be 0, it means this term goes away, right? So if this term goes away, then what we have is just minimize norm of W square by 2 over W and epsilon. And what we are saying we are allowing every W. So if that's the case, when we have to just minimize this, then I know W is equal to 0 was the feasible solution, right? So W, which is 0. So here 0 will belong to RD. I mean, this W will belong to RD. So W is a feasible solution in this case, is the solution, right? And what we had seen is when C is equal to infinity, right? So in case my C becomes infinity, but what my problem was is to minimize this term, right? I wanted to minimize this term. And if I'm saying my C is infinity, it means you won't get a trivial solution for this problem. So the only way this problem can become trivial only when my epsilon I becomes 0. It means you're not paying any bribe, right? So when my epsilon becomes 0, this term goes away, right? And this term also goes away. So what we get at the end is nothing but the hard margin SVM formulation, which is minimize half of norm W square subject to the constraint that my W transpose Xi Yi is greater than equal to 1, which is exactly what we had seen for the hard margin SVM, right? So what we saw is when C is infinity, my epsilon has to be 0 for the solution to be feasible. Then in that case, this is nothing but a hard margin SVM formulation. So till here, it was fine. Like this is where we had ended week 10. So any doubt you had here?
No, ma'am. Clear.
Okay. Um, so next, we are going to like see. So when we were doing the hard margin SVM, we had looked at the primal formulation and how we used the method of Lagrangian to convert our problem to the dual, and we came to the solution, right? So the same thing we are going to do over in this case also. So my problem is this, which is min of half of norm W square plus C times epsilon, somewhat epsilon I. And there are two constraints over here. So one is W transpose Xi Ya plus epsilon I greater than equal to 1. But you also have this epsilon I greater than equal to 0, right? So that is also one constraint that we have. Okay. So I'll just write it in the second line. So this is our problem. Now, if we have to write it in the form of, if I want to convert it to min-max problem, right, or max-min problem, how do we do it? The first thing will be that we should know how to take the Lagrangian, right? So can someone tell me what is going to be the Lagrangian function here?
Uh, Lagrangian is going to be uh, half norm
Now
of W square plus we can introduce alpha and beta I for the
plus C into summation of
Yeah, someone
Double epsilon
was.
plus alpha into 1 minus W
Hmm.
transpose Xi I plus epsilon and minus beta I epsilon I.
Huh. So we have to convert this constraint in the form of g of xi to be less than equal to 0. Something in this form we have to convert, right? Not xi, g of w. We have to convert it into this form, right? So what we will get from these constraint is, I mean, we can write this as
1
1
minus
minus w transpose xi yi
minus
minus epsilon
epsilon
I
I
to be less than equal to 0, right? And the second one, we can write this as
minus epsilon is
minus
less
epsilon
than
I
equal
to
to
be
0.
less than equal to 0. Okay, this is my constraint. Now, if this is a constraint, I can write the Lagrangian function, which is my L of. So, what all parameters do we have? We have our variables are W and epsilon, and the two parameters that we are going to take is let's say alpha beta. Now this is going to be, so whatever the objective is that we need to write, so half of norm of W square plus C time sum over epsilon I varying from 1 to n, plus Now we have to take, since there are how many, I mean, I will vary from 1 to n, right? So you will have for both the constraints. So for the first constraint, you will have I of alphas, and for the second constraint, you will have I of betas, right? So so what we can say this is sum over I varying from 1 to n, alpha
Alpha
I,
I.
1 minus W transpose xi yi minus epsilon I, right? Now the second one would be plus sum over beta I minus of epsilon I, the minus of epsilon I varying from 1 to n. So this becomes my Lagrangian function. So now once we have this Lagrangian function with us, we had seen, I mean, we had seen the proof in the previous week. Like, how can we write this min of, I mean, this, how can we formulate this in the form of min max, right? So this can be written as, so my, whatever the problem was, this problem was, this can be written as min of W epsilon max over alpha I beta I, right? And remember that these parameters that we take, they have to be positive. Okay, so here alpha I greater than equal to 0, beta I greater than equal to 0, and here we just have to write our Lagrangian function. Right now, using the duality, this we can write as max over alpha greater than 0, beta greater than equal to 0, and min of Lagrangian function.
W comma epsilon.
Yeah, W comma epsilon. Yeah. So this is happening because of duality. Now, if we are able to write my problem in this way, then you see that solving this problem is little easier. Like, we'll see. So here, what we have on the outside is max over alpha and beta, right? So if you fix your alpha and beta, so you fix your alpha and beta, you fix alpha and beta. So if you fix alpha and beta, you can differentiate with respect to first with W and then with epsilon. So we'll do dou L by dou W, right? Look at this Lagrangian. So what is the derivative of this L with respect to W? It is just going to be
W.
W,
W minus
because this
W.
norm of W square is just W transpose W, right? You take the derivative, it just 2 times W and it gets cancelled out from the denominator. So we just have W. Uh, we just have W over here. Something.
W
Yeah.
transpose ఉంటుంది.
No, W.
W
So
minus summation.
yeah, then the second term does not have W, and then I directly have it over here. So that would be
alpha xi y.
minus of
Summation I going to from 1 to n.
summation I varying from 1 to n,
Alpha
alpha
I
I
Xi y.
W
xi
W
yi,
X I
xi
Y.
yi, right? Xi yi. Okay.
Equal to
And
0.
this, now we set this to 0. So this is just going to be my W star to be where we have fixed our alpha and beta. So this is just sum over alpha I
xi by i.
xi by I. And we had seen that this whole term can be written as xy alpha, right? So this way we got the w. Now the next variable that we have is my epsilon. So we have how many? We have some ith epsilon, right? So now we'll differentiate my L with respect to some epsilon I, right? So if we differentiate with respect to epsilon I, see the first term does not have epsilon I, so it stays 0. The second term, you see that this sum over epsilon
C.
I means what? It is just
For each
epsilon 1
I.
plus epsilon 2, so on till epsilon n. But we are differentiating only with respect to epsilon I, right? So that is just going to be C.
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 Okay. Now in the third term, you have epsilon I minus, minus alpha I epsilon I. So this is just going to be minus
Minus
alpha I,
alpha I
right?
and minus beta I.
Minus alpha I. Now in the last term, it's just going to be minus
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 beta
beta
I.
I.
Minus beta I. Now equate it to 0. And what we get is
Alpha plus
that
beta I.
alpha
Equal to
I plus beta I is equal to
Equal to C.
C. So this is what we get. And now once we have this W star and this relationship between my alpha i's and beta i's, we can just put this W star into this Lagrangian. So we'll put it here and we will get, so basically we are solving the dual problem, right? So at the end, like when you put this, when you solve this Lagrangian and you found this value of W star, you put it here, and the problem that we get after this is max over alpha greater than equal to 0, beta greater than equal to 0, um, and basically this thing. So whatever this W star we get, which is xy alpha, we will put it here in the Lagrangian. So once you put it inside the Lagrangian, we get the final answer as alpha transpose 1 minus half alpha transpose y transpose x transpose x y alpha. And we also will use this relationship because we have gotten this alpha I plus beta is equal to C. So we have alpha plus beta should be equal to C. So this becomes our problem now. Now we have to solve this problem.
Alpha plus beta equal to C1, right?
What is C1?
C
Just
multiplied by
means
the
that for each it's like a
each
matrix of.
alpha and each beta, the sum is C. C is a constant, whereas alpha and beta
C
are
is,
vectors.
no, that is fine. No, what are you saying here?
C into the one vector.
Or C into the one vector. Okay, okay. That is okay. Okay. All right. So this is the problem we wanted to solve. But one more thing, that my alpha is greater than equal to 0 and my beta is also greater than equal to 0. And this is the relationship between the alpha beta and the C. So if we put some restriction, I mean, if we want to write this constraint in the form of just alpha, this constraint just become alpha lying between 0 to C. This is the constraint that we get. So it's like when you take beta to be 0, your alpha is just going to be C. You take beta to be C, your alpha is just going to be 0. So in a way, your alpha is just lying between this 0 and C. It is bounded between this 0 and C, right? So my the problem
This
hmm,
Ma'am, this expression we got in hard margin also. Same
This
expression we have got.
same expression, yeah, we got the same expression. So the same expression we had got when we were doing this soft hard margin SVM, right? The only difference is that in hard margin SVM, so I will just write it over here. So for the hard margin SVM, mm,
There was no upper bound.
yeah, so it was max over alpha greater than equal to 0, right? So alpha was just positive. I mean there was no limit for alpha. It can go till infinity too. And inside it was alpha transpose 1 vector minus half of alpha transpose y transpose x transpose x y alpha. So this is what we had seen in hard margin SVM. So the constraint that we are seeing is the only difference here, right? And in soft margin SVM, we have um, max
Like
over
this additional constraint is there in soft margin. Alpha
half.
is less than C.
Yes. Okay. So yeah. So this is a problem now we had to solve, right? So how do we proceed now? So this is the dual problem that we have. Now the problem becomes this. So you have to solve this with respect to this parameter alpha. So just look at over here. So just one observation is, if you take C to be 0, then what happens?
Alpha is equal
Alpha
to
is equal to 0.
Alpha is equal to 0, right? So if alpha becomes 0, then
W also becomes 0.
W star is 0.
W star becomes 0, right? And why is that?
because it is the multiple of alpha.
Yes, because it is just the multiplication of these alpha, right? I mean, alpha is a scalar that determines your W star here, right? So yeah, so W star becomes 0, and this is exactly what we had seen when we have written this formulation of soft margin SVM, that when C is 0, W is equal to 0 is the only solution. And when C becomes infinity, it is nothing but
Hard
this the
margin.
same case, right? It becomes the same case. So when C is infinity, we have the hard margin case. Now coming back uh, to this problem, so you will get two complementary slackness condition here, right? So let's say, so my primal problem was, so this is the primal, and let's write here the dual. So my primal problem was, yes, Saurav?
Ma'am, the C is a scalar or vector?
C is it's a hyperparameter. It's a
Scalar, scalar.
scalar, yeah.
It is common for all alpha beta.
Common for all alpha beta, has it?
There is a alpha
Yes, alpha
beta.
beta also scalar.
Alpha and
No,
beta are
no.
vectors, but alpha I plus
For
beta
each
I,
height, for one
They
each
are
alpha
hydrogen,
and
yes.
each
they
beta
are
I, the sum
scalar.
is equal to C.
See, that is common for all the
Each
alpha, all the i's. Irrespective of
For
the
one
i's, the sum will
iteration, it
always
would
be
be
the C.
scalar.
no, no. So alpha I plus beta I is C, where alpha I and beta I are scalar, right? Because we had a total of n constraint for each. No, no, every constraint that we had, where I was varying from 1 to n. So you will get, I mean, when I'm writing alpha I over here, So this varies for every I, right? So you have a vector alpha, which is alpha 1, alpha 2, so on to alpha n. Then you have beta similarly, which is beta 1 plus beta 1, beta 2, so on till beta n. And what we are saying is uh, any I that we choose, for any I, my alpha I and beta I is coming out to be C.
So C is a constant, ma'am.
C
This
is a
will all for any I
constant.
it
This
will
is a
remain C.
constant.
Okay.
Yeah, this is a constant.
Constant scalar.
Hyperparameter.
Yeah,
Hyperparameter.
it's a hyperparameter.
I think you should write C into 1, right? C into 1 vector. That will be much more
Much more clearer.
accurate and
Yes,
Yeah,
accurate.
right.
yeah. Okay. Just okay, yeah. I don't know if this. Then it will be. Yeah, this is fine. Um. Okay. So, all right. So now we are going to look at the complementary slackness condition for the soft margin SPM. So the primal problem was min over W and epsilon of half of norm of W square plus C time sum over epsilon I, where I is varying from 1 to n, subject to the constraint that W transpose xi yi plus epsilon I is greater than equal to 1 for every I, and epsilon I to be greater than equal to 0 for every I. This was the primary problem. And the dual problem is what we have written over here, right? Which is max over alpha. Um, let's just not write it again. So this is a dual problem, right? So let's say at optimality, right? So suppose for the primal problem, the solution that we get is W star epsilon star, right? And for the dual problem, the solution that we will get, let's say, is alpha star and beta star. So alpha star and beta star. So these are the two solutions that we get. Now, what does complementary slackness condition says is at optimality, at optimality, my W star, so for every I, my alpha I star times this thing, which is 1 minus W star transpose xi yi minus epsilon I star is equal to 0. Okay. And the second condition says that for every I, now we have to look at the second constraint. It says for every I, my beta I star times minus epsilon I star should be equal to 0. Right? So these are the two solutions. The complementary slackness condition says these two things. So at optimality, these things will hold. Now, if this holds, we have what we saw is that my alpha should lie between 0 to C, right? So what we saw is that my alpha lies between 0 to C. Now, this W star is nothing but sum over alpha I star xi ya. This is the solution, correct? So if this is the solution, I know the alphas which are positive are uh, are the only the data points for which alpha i's are positive are the only points um, which are going
Will
to
it be
affect my W
alpha
star.
star I? Alpha star I?
It will be alpha star I. Yeah, yeah. So we know that only alphas which are positive um are going to um
Influence W star.
yeah, influence W star, right? So now if you have, in this case, if alpha lies between 0 to C, then what happens? You will have three different cases that will arise from here. So the very first case that will it can happen is my alpha I star can be exactly 0, and the another extreme case is that my alpha I star is exactly C, right? Now the second condition can be my alpha I star belongs to 0 comma C, open interval 0 comma C. So these are the three cases that arise. Now what we are saying is, if alpha I star is equal to 0, I know this is not going to these data points are not useful to us, right? These points are not useful for W star. For my weight vector, these points are not useful, for which alpha I star is equal to 0. So what happens if my alpha I star equal to 0? If my alpha I star is equal to 0 and I know that alpha I star plus beta I star should be equal to C, right? This is the condition that we had gotten. So if this has to satisfy and my alpha I star is equal to 0, then in that
Beta star
case, my beta I star has to be equal to C, right? Now, if beta I star is equal to C, then from the complementary slackness condition, I can say that my epsilon I star has to be 0, right? Because my beta I star is positive. So if my beta I star is some value C, then in that case, I will say that my epsilon I star is equal to 0. This is happening from complementary slackness condition 2, right? So we got beta I star to be C, epsilon I star to be 0. Now, the constraint that we had was my W transpose Xi Ya plus epsilon I has to be greater than equal to 1, right? So the constraint was W star transpose Xi Yi plus epsilon I star has to be greater than equal to 1. This was a constraint. Now, if epsilon I is 0, then what we get is my W star transpose Xi Yi to be greater than equal to 1 is what we get, right? So these are the points which are outside my hyperplane, right? These are outside my hyperplane.
It can also be on the
It,
plane.
yeah, because there is equal to 1 also. So how will it look like? So suppose if this is my W star and this is my decision boundary, and let's draw the hyperplanes. So let's say these are my hyperplanes, and this we are saying it as set of all W's, so, sorry, set of all Xi's such that my W star transpose Xi Yi is
equal to 1.
Equal to 1.
is equal to 1. Sorry, is equal to 1. and this point is set of all xi's such that w star transpose xi yi is equal to -1,
Is
right?
equal to 1 only, ma'am. Yi it is there, no?
Yeah,
Yi you have to remove. Remove the
Sorry, sorry.
yi, ma'am.
Correct, correct. Sorry.
Yes, yes,
Yeah,
ma'am.
1. This is -1.
so,
Okay.
ma'am, it is going to be 1. Okay, you removed y. Okay, you removed y.
Yeah. So basically, this is the reason that we get this also. I mean, this is also here. Okay. So this is the reason. So the points which lies here, they are not important to us. That is what we're trying to say.
Some of the points that lie on the line may
They
be,
they will
Important.
become. We'll see in the next case
not all
because
the points that lie on the line will be included in this, right? Some of the points may be included, but some may not be included in this,
true.
that lie on the line,
Hmm.
that lie on the hyperplane.
Yes. So this was the first case, and we are saying such points are not very important for my W star. Okay. Now, what happens if alpha star belongs to 0 C? This will mean that my beta star should also belongs to 0 to C, right?
Yes, ma'am.
And if this happens, then from complementary slackness condition 2, my epsilon I should be again 0. This will imply that epsilon I is 0, right? So if this is 0, what we can say is, yes, this is 0 and alpha star should, if it belongs to 0 comma C, this has to be 0, right? So it means
Yes.
that my W 1 minus W star transpose xi yi minus
0.
epsilon I star is equal to 0. But since epsilon I is 0, this will also go away, right? And what we get is W star transpose xi yi
Y
is equal
1.
to 1. So the points which are
Support
exactly
vectors.
on the hyperplane, they are important to us. Okay. Now the third
So the
case,
points that lie on the hyperplane, some of them will have alpha is equal to 0, and
some
some
of
of them
them,
will have alpha is equal to non-zero, right?
right, right.
Okay, right.
Hmm. So like if from here we see my alpha I is strictly greater than 0 and strictly lesser than C, right? So
Yes, ma'am.
uh, so from here we get the points to be exactly on the hyperplane, and we saw that these points are important to us.
They are support vectors.
Yeah. Now the other extreme case, which is alpha star is equal to C. So these are the points that are going to be the most important to us, right? And now we'll see like where do these points lie, right? So if alpha I star is equal to C, this implies that my beta I star should be equal to 0, right? And if my beta I star is equal to 0, this
Epsilon
means that my epsilon I
should be
star
greater.
has to be greater than equal to 0, right? This is coming from here, right? So epsilon I star has to be greater than equal to 0. Now, if epsilon I star has to be greater than equal to 0, and I know that my 1 minus W star transpose xi yi minus epsilon I star is equal to 0, then this thing has to be greater than equal to 0. because this is exactly equal to epsilon I, and epsilon I is greater than equal to 0. So this has to be greater than equal to 0. And this will mean that my W star transpose xi yi should be less than
Less
equal
than
to
equal to
1. And where do these points, where will these points lie? So right, so this is my W star. This is my decision boundary, and these are
between the
my
hyperplanes.
hyperplanes, right? Explain once more third condition. Okay. Um, so the third condition, see, alpha I star is equal to C, right? So if this alpha I star is equal to C, we know the relationship between alpha, beta, and C. So if this holds, my beta should be equal to 0. So beta I star is equal to 0. Now, if beta i's are equal to 0, we can say that my epsilon I has to be greater than equal to 0 due to complementary slackness condition, because this has to satisfy, right? So that's why we can say my alpha I star has to be greater than equal to 0. Now, if this holds, then from the first complementary slackness condition, which was this thing, I can say that my epsilon I star has to be equal to this term, right? But if epsilon I star is greater than equal to 0, it means my 1 minus W star transpose xi yi has to be greater than equal to 0. And from there, we get this condition. Okay. So once we have this condition, uh, so what this is going to be, this line is my set of all xi such that my W star transpose xi is equal to 1, and this is set of all xi for which my W star transpose xi is equal to minus 1, right? So W star transpose xi yi less than equal to 1. So we are saying less than 1, right? So this
Yeah,
will
so
be
in the
on this
margin,
side.
either mistakes or in the within the margin.
Yeah.
It will not go outside the green line, ma'am.
Yeah,
No,
it
it will
won't go
go
But
outside
inside
the
left
for
minus one
side.
line.
misclassified points also, it will be
Yeah,
less than minus
misclassified.
1.
Yeah.
What?
For misclassified points, for example, if there is a negative point in the right side, negative
Mm-hmm.
point on the right side, or there is a positive point on the left side, that will be also included.
Yes, those will be also included. So this is just W star transpose xi yi less than 1, less than equal to 1. Sorry, W star transpose xi less than equal to 1. Now there will be W star transpose xi greater than equal to minus 1, right? And that will be on the other side.
It
So
will be within the margin,
on this side, right?
but it won't go outside the green line, which is a positive margin.
If there is a negative point there, then it will have it will if on the positive side there is a negative
Mm-hmm.
point,
Mm-hmm.
Yes.
then it will be included.
Yes. Yes. Yes.
Yeah. So I'll just this is just become very messy, I think. I'll just do a simpler here. So this is my W star, and I know this is my decision boundary, right? So if, and anything here is positive and anything here is negative is what we know, right? Now if we have some point from the some positively labeled point can be here, right? So they are on the right side of the margin, but they are not classified correctly. I mean, um, they are not
Not
correctly
less than
classified.
one. They are not
Enough
greater than
margin.
one.
Yeah, it's not enough margin for this um, to say, right? So these are the points which are important to us. Now it is also possible that it is on the wrong side. So let's say this point is on this side. So again, this point is not correctly classified by this W star, right? So the points
Or
like
if
this,
plus is on the left side also, left side of the
it can be on the left side
yes.
also. Yeah, and from this side also we can just have some negative. I'll just do this, something like this. So we can have some negative here, or we can have some negative here, right? So the points which are not correctly classified, or the points which are classified
With
correctly
enough
but
margin.
not with enough margin, then those cases are important to us, because for these points my alpha star is the maximum. They are contributing most towards my W star. Okay. So we'll have cases like this.
Again, so the points that lie on the hyperplanes can have alpha equal to 0 also, alpha between 0 and C also, and alpha equal to C also. So points on the hyperplane can have alpha equal to any value. It can be
Ha,
0
ha.
also,
Yeah,
between 0 and C also, and it can be C also.
right, right.
Right.
Yeah, correct.
Only in the third case we have some bribe involved. Other cases we have epsilon is 0 because they're already predicting correctly.
Only in the last cases, yeah, that's true.
Epsilon greater than
Because
equal to 0.
because in the first case, it is um, 0, right?
Epsilon is greater than equal to 0 because beta is 0. Beta is 0. That's why epsilon is greater than or equal to 0.
In both, if you see here, both cases, your epsilon I is 0, right? Here and here. Only in the last case, we have epsilon I to be greater than equal to 0. So this was about the soft margin SVM. So there is also the primal point of view that has been done. Like how do we like once this W star transpose Xi yi, if we split it in three different cases again, like it is less than 1, it is equal to 1, it is greater than 1, right? Then how is it? I mean, how does this alpha i's and beta i's changes that we have also seen? So I would suggest. So, is there any doubt in that part? I mean, both are the same thing. You'll get the similar thing. If you have gone through it, do you have any doubt in understanding that the
No,
primal
ma'am, clear.
the primal point of view that has been done? Okay. Okay. All right. So, in summary, like what we had seen was if my alpha I star was 0, then what we got is that my W star transpose xi yi has to be greater than equal to 1. If alpha I star lies between 0 to C, then in that case, my W star transpose xi yi has to be equal to 1. And if alpha I star is equal to C, then my W star transpose xi yi has to be less than equal to 1. Okay, so this is what we saw. Any doubt in soft marginal sphere? Because then another two topics that are coming in is completely different. So before we move to that, if you have anything you want to discuss here, you can let me know. Okay, I'll move to the next topic. So the next topic that we have in this week is what is overfitting and underfitting of the model. Overfitting and underfitting. Okay. So when do we call? So when do we call that a model overfits the data? Does anyone um, like? Can
When
someone
it
tell me?
is
Hmm.
when it is too close to the training data, then it won't be able to predict the test data well. That means it took the noise as well. It
Hmm.
tried to fit
That
the noise as well. So in the test data, it is not predicting very well, because in training data we had like error almost equal to zero. It was exactly fitting, so it
Hmm.
was not able to generalize the data to any other data set.
Hmm. Yeah, that is overfitting, right?
Like the depth is too large in a decision tree, or like the lambda is too low in the Gaussian case we took.
Okay. Yeah, so that's correct. That's what we mean by overfitting. So, like when you fit your model to a very great extent, like um, you're trying to you fit the model in such a way that your training error has become almost zero, right? So when things like that happens, your model won't be able to generalize well on any new data set that you give to the model, right? So if it might happen that you're trying to reduce your training error and you're trying to fit as much as possible on the data set, but doing so can impact its performance, like how it performs on a new data set that you give. So cases like this is what we call as overfitting of the model, right? So that is my overfitting, and underfitting is more like uh, so you are not able to. So what you're trying to do is some very complicated model. You have some complicated model, and you're trying to do a very simple. You're trying to fit a very simpler model on that. Let's say you had some uh, maybe distribution like this, right? But what you're trying to do here, or not the distribution like this, you observe the data set, which let's say fell on and something like this. I mean, it has a shape like this, let's say. So you just look at this data set, you're not looking at the structure. So if you are only looking at the shape of this, I mean, you're only looking at this data set, what in real it has come from this structure. I mean, this sinusoidal wave is something that is a true structure in a data set. But looking at this data set, what you did is you try to fit a very simple model. Let's say I fit a simple linear regression model. So this is a very simplest structure that we have tried to fit. So cases like this is where we are trying to this is a very simple model we're trying to fit. So this is what we call underfitting. Okay. So what happens in underfitting and overfitting is, like, when you overfit the model, like you overfit to such extent, like if you're given this data set, maybe you fit it like in this way. Suppose this is how you fit this. So doing this, you're trying to make your training error to be exactly 0. But any like you get some new data set, again you fit this, right? You will get a very high variance in such cases when you try to overfit your model. So yes, underfitting both training and validation losses are high. Overfitting training and validation losses decreasing with the validation loss increase while training loss keeps on decreasing. Yeah, that's true. Maybe I should draw two different vector over here. So this is my true structure. And here we will draw the, let's say the underfit model is what we are going to draw. Okay. So these were my data points. And what we fit over here is, let's say this. Okay, this is what we fit. Then in this case, the error that we will get is, these are my error. Right? These are the errors that we get. Now, what about when you overfit the model? So we have the same set of data point. And let's say we got something like this. Something, okay. But now if you compare it with the like what the original value of y was, you will see that the error that you will get in case of the overfit model is going to be quite high. So now if you take some different, I mean, if you train your model on some different training data set, the model that you fit, the variance is going to be quite high. So in case of overfit model, the variance is quite high. And in case of the underfit model, the bias is quite high, is what we say. So in the underfit model, the bias is high, and in the overfit model, my variance is high.
Means that if you change the training
If
data
you
set,
change the training data
then
set,
you will get a different. If you
different
overfit, then you will get a different curve,
different curve,
which will change the predicted value of the test data
which will change
to
the
be.
predicted value of the test data. That's true.
Yes.
So if you fit this, let's say on some different training data set, you fit the model. You are maybe say, let's say this was my X test. I mean, for this one, I'm going to predict. Let's say my Y is here. My original Y hat should be here. Okay, and for some, if I fit this on some different training data set, maybe let's say I get some different curve, and maybe I get the curve goes something like this, and then it's a very the error is quite high in this case, right? I mean, the variability is quite high between these two errors,
Between the values of the test data,
Y
the
test and
variance
what
is high.
uh, this Y test and F hat of X test. Right? There's going to be, for different data set that you take, the variability is going to be quite high. The amount by which this F hat will vary is going to be quite high. So that's why we say the variance is high in the overfit model. Okay, but in the underfit model, my bias turns out to be quite high. Okay, so what we want is, we want to have some sort of balance between balance between this bias and the variance. And you would have studied the bias variance trade-off also, right? So you would have seen this expression, which is expected value of y minus f hat of x, right? If you find the expectation of the this term, this turns out to be nothing but variance of your f hat plus bias square of f hat is what you get. So you want to have a less variance, you want a model which has less variance and less bias. So you sort of try to balance these two. Like, this is our goal. This is what we want to do. We want to have a balance between these two things. There is also another term which is something which we call an irreducible error. So I will not go into that. So let's and this irreducible error is something that we don't have any control over. Okay, so the only thing we can control is this, like, how can we minimize our variance and minimize the bias. So there are two techniques that we are going to see over uh, after this, that will help us understand, like, how, like, what different way we can use to minimize this variance and minimize this bias. Just give me a minute, I'll be back. Okay. So, all right. So the two different techniques that we are going to see, which will help us dealing with this bias variance trade-off, is one is bagging and other is boosting. One is bagging and another is boosting. So the full form for bagging here is the bootstrap aggregation. So before we start with the bagging technique, we'll just see one small example, like uh, how doing the averaging is helping us in minimizing the variance, right? So we have seen this, that if you have some IID sample, which is from, let's say, coming from some distribution, right? And for simplicity, let's take it's coming from a normal distribution with parameter mu and variance 1, right? So here what we had to estimate, since mu is something that we don't know, so we'll take we'll take samples and we will try to come up with estimators of mu. So suppose we define one estimator of mu to be x1, the very first sample of, so whatever the first sample I get, I am calling it as my estimator for mu1 hat, estimator for mu. Now, the second estimator that we can define is, let's say, x2. All these are valid estimator, right? Because we know the estimator is nothing but a random variable, right? This is a function of random variable. So all these are valid estimator that we can take for our mu. Now, similarly, I can go ahead and define my mu1 hat to be um, xn, right? So we can do this. All right. So when we take the expectation of each of these mu I hat, what is this going to be? It is just going to be expectation of xi, which is nothing but mu. So for every I am getting the expected value of mu to be exactly equal to mu, right? So all these estimators that we have defined over here, we can call these estimator to be unbiased estimator, right? Remember what was the unbiased estimator? Unbiased estimator was, if I have an estimator, if I have a parameter theta, and let's say my theta hat is the estimator for that parameter theta, and if I have to check whether this estimator theta hat is unbiased, I will check if this is exactly equal to theta. If this hold, I will call it as unbiased estimator, right? All right. So so what we saw here, that all these are unbiased estimator. Now, if we had to, I mean, those are all those are valid estimator, all those are unbiased estimator. Now, if we had to go through the technique of if like technique of this ML estimator, let's say I wanted to find the ML estimator, then I know that this W hat ML should be nothing but the sample mean, which is sum over xi divided by n. This should have hold. And if I define my estimator mu hat ml to be x bar, then in that case, I know that expected value of this mu hat ml is mu, right? This is mu. And the variance of this mu hat ml, if what we get is sigma square, which is in this case is 1 divided by n, right? This is what we will get. But if I look at the variances of each of these individual estimator, like mu1 hat, mu2 hat, mu3 hat, so on till mu1 hat, right? The variances of all these estimator, though these estimators are unbiased, that is, their expectations are coming out to be mu, but their variant, when we look at the variances, they're all going to be 1 1, right? So what we saw is that if we take the average of these estimators, so if we take the average of so x1, x2, xn, all these estimators, when we took the average of these, the variance has reduced, correct? Okay, so this is the idea that we're going to see in the bagging also. So when you take the average of these estimator, the variance is going to reduce. So basically what we are saying is this averaging will help us in reducing the variance. So bagging, what it does is it reduces the variance basically. Now the idea for this bagging is that suppose you have this data set. You have x1, x2, so on till xn. Or maybe let's just okay, let's say we don't have just one data set. Suppose we have some m different data set. So we have d1, we have d2, and we have m data set, right? And each of the di looks like this: x1, um, this I is to denote okay. Okay, so what I'm trying to say here is that let's say you have m different data set, and each data set has n data points. So my d1 should have my x1 y1, so on till xn by n. Okay, my d2 should have again x1 y1, so on till xn by n. So here 2 is to denote that it is coming from the second data set. So you will have every data set, we are saying each data set has n data points, right? So if you have this m different data set, so what we are going to do is we are going to train my model. So any model we are going to fit on these data set. So let's say we are going to go with decision tree. Okay, so let's just let's just fit this decision tree in such a way that it has overfit the model, right? So in every data set we are going to overfit the model. So let's say on the first data set we have a decision tree, and let's the model that we get is h1, and all these are overfit model. From the second data set, let's say we got h2, and from here we get hm. So we get these classifiers, and what we are going to do is like here we saw that um, once we average all the estimators, we will reduce the variance. So the classifiers that we have it over here, which is h1, h2, hm, and these are obtained by overfitting the decision tree on these m different data set. So if we aggregate this, and we get a classifier over here. So one h star is going to be my sine of how many classifier do we have? I'm going to take the average of this, which is 1 upon m, and we take the average of hi of x, where I is varying from 1 to m. Okay, and this is the average that we're talking about. So we had taken the average of all these classifier, But since we're talking about a decision tree, which is a classification problem over here, so the final classifier is going to take the sign of whatever you get here, and based on that, it is going to predict, right? So this is the final
X is
classifier.
the here X is the test data point.
X is the test data point here.
Okay.
Hmm. Right?
So you have to
So,
make X go through all the different classifiers,
huh,
and then you have, whatever label you get, you have to make a average of all the labels, and the
yeah,
sign of that label is going to be the what do you
yes,
say, the
sign of
final.
that is going to be my the final prediction.
Okay.
So what we are trying here is we are trying to say that uh, doing this, I mean, taking this m different classifier and taking the average of all this, and then predicting uh, the final value of then predicting this um, the value for X test. I mean, this is in a way is going to reduce the variance. Okay, so that's the idea. So we started with m different data set, but now how is this like what is, I mean, we in the initial we had said bagging is bootstrap aggregation, right? So where is this bootstrap coming into the picture? So that we have to see now, right? So this is the idea of the bagging in a way. So here we have m different data set, but we know that in reality we won't have so many data set available to us, right? So we will be given just one data set, and from there, is there any way we can try to create different versions of the data set, right? And each data set should contain the same number of values. So like here we said I have d1, d2, dm, and each of this data set had m different had n data point, right? So the size of each of the data set was n that we had seen. Now, is there any way that given if I'm given a data set which is suppose x1 y1 x2 y2 so on till xn yn. So if I'm given this data set, is there any way I can come up with m different data set from here, right? This is what we are trying to do. So if there is a way that we are able to come up with m different data set from the given data set, then we can again repeat the same process. Like we can overfit some model, we get the final classifier for each of the from each of the model, and we take we segregate it, and we take the average of all these classifier, and on that we predict basically. So the process of getting these m different data set is what is where the bootstrap is going to come into the picture, right? So does anyone know what bootstrap is? Okay, so bootstrap is basically what we are doing is we are sampling with replacement. So bootstrap is sampling with replacement. Okay, so let's just write d to b. So I'm just going to write x1 by 1 as capital X1, capital X2, so until capital Xn. All right. So now we have to create m different bags. So what we will do is from this data set, we pick one point, and we randomly pick one point and we put it into, let's say, the first bag. Suppose I get some x1, or not x1, let's say some, I get x10. All right. Now I put this point back into the bag. Okay, and then again I pick one data point from there. Let's say I get x32. Let's say n is equal to 50. Okay, then again I put this back into this and I get some other data point, and let's say again I get x10. Right, it is quite possible because this is with replacement. So again I get x10. Again I put this back, and again I take some data point, and let's say I get x9 something. So I will keep on doing the same thing. We repeat the same thing and again uh, until we get in my bag 50 data point, right? Because my n is 50, my original data set has 50 data point. So I have to keep on repeating this process until we get 50 data point in my bag 1. Same process we'll do for bag 2. Yes. Bootstrap. All right. So we'll keep on repeating this process for for the bag 1 until we get 50 50 data point in my bag 1, and we'll do the same thing for bag 2. We'll do the same thing for all the bags. So at the end, what we will have is each bag will have n data points, but it is quite possible that any of the bag can have some repetitive values, right? It is possible, like as we saw in this case, that x and k appear twice here. So there are many data points that are going to be repeated in any of the bag. It is possible. So, but this is helping us in creating m different bags of n data points, right? So this is what is called the bootstrapping technique. So bagging, which was bootstrap aggregation, this is what we mean by bootstrap. And now where the aggregation is happening, so we had this data set which originally had endpoint, and from there we were able to manage to get m different bags. We were able to create data points of m bags of n data points, right? So we created d1, d2, so on till dm, and each had n different points. Now we'll repeat the same process. We overfit the model on each of these data set, and let's say I get the classifier h1, I get h2, and so on till hm, right? And at the end we segregate everything, and we get h star x to be sine of 1 upon m sum over hix, right?
I going from 1 to m, right?
I varying from 1 to m, right? So yeah, so uh, what we had seen is that some data points are going to be repeated, right? So the probability that we get that for any data point belongs to a bag is turns out to be some roughly 67%. So you can check this. So what we get is the probability that a data point appears in a bag is roughly 67% or 0.67 is what we can say. The proof has been given in the lecture. You can take a look. Now there, after this, um, uh, so till here, is this, are you able to understand? Is it okay?
Yes, ma'am.
Okay. So after this, you have the concept of random forest coming in. That I'm skipping for now. I will take it at the end. Um, so, like, it's an extension for the bagging only, like where we wanted our classifier to be more uncorrelated. I will come back to that. So, this was about the bagging. And the next technique that we had seen is boosting. Okay. So, a very popular method over here is AdaBoost algorithm. So, I think one thing I forgot to mention is like, yeah. So, what we like, there is like the idea for this bagging and boosting was like, you take, we wanted to understand how to deal with this bias variance trade-off, right? So what they're trying to do is they're trying to start with some weak learner and they convert it to the strong learner. Okay, and such kind of classifiers are called the ensemble classifiers. And this is what both backing and boosting are trying to do. So like, we start with some weak learner, meaning that any classifier that performs just better than any random classifier. We start from here and we convert it to some strong learner.
So both underfit as well as overfit both come under weak learners, right?
Both underfit and overfit come under the weak learner, because we see like, when one has high bias, one has high variance. So we want to sort of kind of balance it. So in AdaBoost, what we are trying to do is in AdaBoost algorithm. So where in bagging we first did like we started with the bootstrapping and we created the bags, and then we aggregated it and found our final classifier. In AdaBoost algorithm, we are trying to do it in a different way. So here, let's say if I have a data set given to us, which is x1, y1, x2, y2, so on till xn, yn. Okay. If this data set is given to us, where xi is again in RD and yi is in plus minus 1, let's say. So what we do in AdaBoost algorithm is uh, all the data points are first assigned the equal weightage. Like, each data point gets a uniform weight. So since we have n different data point, what we will say is each of the data point for the distribution is going to be uniform. So 1 upon n, 1 upon n, so on till 1 upon n. This is the distribution, right? So we initialize d naught. So d here we are representing to denote the distribution. So d naught of I to be equal to 1 upon n, because we had n data point and we are giving equal weight to all these data point. So the distribution is 1 upon n. So this is how we initialize. Now The idea over
This
here,
means that we are including 1/n of every data point in the.
no,
Uh,
like every data point has this. I mean, every data point has the chance to get selected in the next round. It's like that. I mean, everything has a uniform weightage.
so how many points we take first? We take n points.
We take, um, I mean, let's say if you start with, let's say, decision tree, right? Then like when you are when you are forming that tree, my there every point we are giving the equal weightage.
So in that this for the technique which you taught first before this,
Bragging, huh?
uh, in that we were creating m different data sets out
Right.
of one single data set, right? And each
Huh.
of these m data sets were having n points.
Yes, each of these had endpoints. Yeah.
So here what we are creating, we are creating a single data set out of these endpoints. Uh, what is this meaning of 1 by n that I did not understand? I mean, what is that?
So now we will sample from this data set. Let's just
Okay.
sample from this data set. And when you're sampling this, I mean, every data point has the same probability of being getting selected.
So that
So,
means we are going to get the same data set in the first round.
because everything has the same weightage. So, if we are going to get the same thing.
Okay.
So, we are just trying to sample from this data set that we have. But here, now everything are given the equal importance. Every data point has the same importance.
And
Now,
we are choosing endpoints. We are choosing endpoints.
we are choosing endpoint. Right. We are choosing endpoint.
Okay.
Okay. Now, if we, this is the initial phase. Now, if I move to the, let's say, the first iteration. So let's say I will do t is equal to 1. This is my first round. So I will take my data set and I will take the distribution. The this is comma, okay. Or uh, I'll just first write this. So let's say I'm going to run it for t different round, capital T different round. So I'm going to take this data set with the distribution dt. Okay, I will, and dt is the distribution that you're going to get for your data set at the time t, right? So the idea over here is that if it is going to correctly like whatever we'll take the example of decision tree only. Okay, so if let's say if we have some data point and whatever question feature value pair you have put, that is able to classify, let's say, some um, if you have 100 points and it is going to correctly classify let's say 70 points and not going to correctly classify some 30 points. Okay, so what you will do is the points which are correctly classified, that for the questions that you have asked, the feature value pair that you have given, the points which are correctly classified based on that question, now in the next round you are going to reduce its weightage. So if 70 points are correctly classified in the next round, what I would want is I would want to reduce its weightage in the next round, so that I don't want to I don't want these numbers to appear uh, more frequently when I'm trying to fit this when we're trying to work on this 30 data point, right? So we'll try to reduce the weightage or the importance of these 70 points that are correctly classified and increase the weightage of these 30 points that are incorrectly classified, so that these points occur more frequently, right? And my model is able to work better. I mean, it's going to generalize better in that case. So this is the idea. So the way we increase or decrease this weightage is by, if you're saying the points which are correctly classified, if I'm going to reduce its weightage, by how much amount we are going to reduce its weightage. So we'll define the distribution T. So in the next round, which is in the T plus 1th round, for the ith data point, we'll take the current distribution, which is dt of I, and we are going to multiply it with e to the power minus alpha t. Okay, so we are so this e to the power minus alpha t is what? This is 1 divided by e to the power alpha t. So whatever the current distribution is, in the next round, this weightage is going to reduce. This is for if your whatever the classifier you got, if this correctly predicts your data point xi, in that case you reduce it. But if it doesn't correctly classify, right? If ht of xi is not equal to yi, then in that case I am going to multiply it with e to the power alpha t. So this is how the distribution is going to look like for my data points. Okay, so if you see, I mean, I am saying that these are the distributions, but
Here, ma'am, just a minute. Here,
yeah.
this dt, in the
Mm-hmm.
case of the first iteration,
Uh-huh.
this dt will be all 1 by n, right? In the first
Yeah,
iteration.
see, d naught is 1 by n,
Right, right.
right? This is how we initializes. Now, let's say in the very first round, you got some classifier. Let's say I got h1 of, I got h1, let's say. Okay. Now, if I'm saying that, and let's say I have some 5 data point. Let's say, for example, I have 5 data point. I have x1, I have x2, x3, x4, x5. Suppose my h1 correctly predicted x1, x3, and x4, and incorrectly predicted my x2 and x5, right? So the distribution of this data point that you are going to get in the next iteration would be, so if I write d2i,
D1, right, ma'am? D0 we got.
d0 we got, right? So d1i, the distribution that you should have is d naught of I
Which is 1 by n.
times, yeah, e to the power minus alpha t. This is for the point x3, sorry, x1, x3, and x4, and you're going to get d naught of I. Yeah, I will write just 1 by n, right? So write 1 by n. So 1 by n e to the power alpha t for x2 and x5. Okay. So if this happens, you can see that since these points are going to get more weightage in the next round of selection. But see, what we are calling this as is that these are the distributions, right? In the initial phase, when we initializes this was just 1 upon n, and we have n different data point. So, I mean, if I add all of this, they will add up to 1, right? And it satisfies that the probability overall, the sum of the probabilities over all I is equal to 1 by n, is equal to 1, right? This holds, right? So it should also hold here, right? right? So suppose I got this. I got d1I to be, I got 1 by n e to the power minus alpha t and 1 by n e to the power alpha t, right? For x1, x3, x4 and for x2 and x5. But now for x1, what is going to be the distribution? This should be 1 upon n e to the power minus alpha t divided by 3 times 1 by n e to the power minus alpha t plus 2 times 1 by n e to the power alpha t, right? Now this is
So
the
this
way,
is actually the D1. This is actually
this
the
is
D1 now.
this is what you're going to give for the first data point.
This is the D1 for the first data
Ah,
point.
yes. Now what about x2? So for x2, I am going to get 1 upon n e to the power alpha t divided by this, and
Same,
this will
same.
stays the same. I will do it for
Denominator
x3,
will stay
x4
the
and
same.
x5. Sorry. So I'll do it for x3, x4 and x5, right? So
And what
this
is
is,
alpha T? What is alpha T
yeah,
here?
yeah. So alpha t I will go for. So alpha t is, I mean, what has been observed is that this alpha t is given by uh, ln of 1 minus error of ht divided by error of ht.
HT is the weak classifier which we applied to
Yes.
the.
Hmm. ht is the weak classifier that we applied. So let's say if it's a if I look at h1 only, so I know that my h1 is predicting 3 points correctly, but not predicting 2 points right? So the error of h1 is going to be what? 2 upon
2
5.
by 5.
Yeah. So what should my alpha t should be? It is ln under
3
root
by
of
2.
3
3 by
by
2.
2, right? And I can just take this as 1 by 2. So I get 1 by 2 ln 1.5. So my alpha 1 is half ln 1.5, right? So this has come from some analysis, and like alpha t is taken as ln of under root of 1 minus error of ht divided by error of ht. Okay, so this is how the distribution in every step of in every round you perform this algorithm. This is how the distribution changes. So every data point which are correctly classified in the next round, those data points are given less importance, and the data point which are not correctly classified in the current round are giving more importance in the next round. Okay, so the final classifier, so from the first time when we perform, we got, let's say, the classifier h1. Then we run it again.
So,
um,
ma'am, this
uh,
is the in the curly brackets that you have shown in the
mhm,
curly brackets here
mhm.
that you have shown. This is the D1, right? D1,
This is d1. Hmm.
right? Now, this D1 with using this D1 on the same endpoints,
Hmm.
you will be getting now H2. You'll be
Now
now
you will
getting
get
H2.
h2. Hmm.
And
Yes.
using this H2 you will apply, and you will
Ha.
see how many are classified, how correctly
Correctly.
classified, and how many are incorrectly
Incorrectly
classified.
classified. Then again you will get some d2.
You will get now, yes, you will get a D2 now using this D1.
Yes.
Okay.
So it will
And
keep on going on. So you will get h1, h2, h3, and you run it for, let's say, capital D round, and you get h of capital D.
so
So
what is the limit for this T, the capital T?
what is the limit
How much?
for? I mean, when you reach to a point when um you are able to correctly predict your data points.
Okay.
Hmm. So let's say you get these classifiers at these rounds at first, second, third, from until the 10th round, you get these classifiers. So the final classifier that we get in boosting, so like in bagging, the final classifier that we had gotten was sine of um, 1 upon n,
Average,
1
average.
upon m, I varying from 1 to m, h I of x, right? This is what we get. So in boosting, what the final classifier that we get h star is sine of sum over alpha THT. So here alpha T is coming into the picture. So T is varying from 1 to capital T. So this is the final classifier is what we get.
And T will depend on how till what time you
So,
get it correctly classified.
so okay, so how so there is a T that has been mentioned. I mean, this has been found. So the limit for T that is given is your T should be greater than equal to 1 upon 2 gamma square ln of Tn. So this is a bound for T that you get.
Where n is the number of data points.
N is a number of data point.
And what is gamma?
So gamma basically decides this is some um, so what gamma decides is like how good your weak learners are. So this has been quantified into this gamma, like how good your weak learner is. That is being quantified by this number gamma here. So if this happens, I mean, if your T becomes greater than this quantity, then what we get is your training error becomes almost zero. I don't know how this proof has come, but it has been observed through. Um, this is what has been observed. So, like if T becomes greater than this value, then your training error becomes exactly zero.
But we are having different learners, right, ma'am? So gamma will depend on the. So for each iteration, we have a different learner, right? For
Uh,
each iteration, we have a
hmm,
different learner, weak learner. So this gamma will depend each time. It will have a different value.
yeah, it
Gamma
should
is
have
the
some different. It should have some different value. That's true. Um, yeah, I'm not sure
are the
how this
learners same.
proof
Are the
has been.
learners same for all the iterations?
No, right? Because every time it's changing. You're getting H1, you're getting H2. These are changing, right? I'm not sure how this gamma has been verified. I mean, obtained. Um, I will have to look into this.
And training error is equal to zero means we are not overfitting. So we are not. Uh, this is like
Then
training error zero means
then we'll start
overfitting, right?
overfitting. Then we'll start overfitting.
Overfitting.
Yeah.
So training error zero means overfitting, right, ma'am?
Yes, training error zero means overfitting. So if this is like the limit for T, so T should be less than this,
Okay.
right? So if this is my T and I'm talking about the error, then um, as the number of iterations increases, my training error is reducing, but at this point, it starts to go zero. And after this, whatever t we get, it will overfit. My training error is zero. This will overfit. Okay. So this is an iterative technique, whereas what we had seen in bagging is like everything can be, all the classifiers can be run parallelly, but here it's an iterative technique. It cannot be run parallelly. Yeah, so this was
So the
about,
final H star that we get, we have to apply
Mhm.
on a test data, na,
We have to apply on the test data. Yeah.
to get the label of that what do you
Mm.
say, test data.
Yeah, yeah, yeah. So it depends on both alpha t and my ht. Yeah, so this was about the boosting. I've skipped random forest for now. I think in the next class I will cover that.
Yes, ma'am. Random forest are left in this session, right?
What?
Random forest will be covered next
Random
class.
forest will be covered in the next class. Yeah, we'll cover it in the next class. So your assignment submission is this Sunday, right? For
Yes.
week 11. Yeah. Okay. Okay. Any doubt? Whatever we
No,
have
ma'am.
discussed. Yeah.
Ma'am, I have a link to explain some slide of the professor.
Some slide from week 11.
Yes, ma'am. Yes, ma'am. Professor gave a link in comment section.
Okay. Which slide you're talking about? This is Ashish Chandulkar's. Okay. This is different prof, right?
Those are the old MLT
Old
lectures.
MLD lectures. Yeah.
Yes, yes, ma'am.
Yeah. So you have to, this is not the correct slide for what has been done currently.
Ma'am, here the weak classifier which we use this to get
Where?
the H1 H2 H3 HT.
Mhm.
This weak classifier is a overfit one or a underfit one.
These are the underfit one, underfit classifier.
So in the earlier case,
For
bagging, we
bagging, we
were
use
using overfit.
overfit, and here we are using underfit classifier.
Okay.
Hmm.
Underfit means
Underfit means you have high bias.
okay. So in the case of decision tree for overfit, we were continuing the decision tree till we get pure data set.
Right.
Pure.
Like, oh,
So if for decision tree, if we apply this technique, we have to ask only how many questions for that? I mean,
maybe one or two questions should be enough.
okay. And how we will
You'll
decide? Okay,
get some idea.
okay. But which question to ask? How we will decide which question to ask?
Which question to ask? We know this information gain or gene impurity. We have these techniques, no? Like, which question will you put for the first node
So first
top
question
node,
that we ask will depend on the maximum information gain that we get.
maximum information gain. Then we
Okay.
proceed. Then again we'll see which question will give me the highest impurity gain, information gain.
So like
Then we
that,
put
we'll
that
proceed
question.
for only one or two questions.
Yeah, we'll proceed only for 1 to 2 questions, and we'll have some decision tree with us, and we'll start from there.
Okay, okay.
Hmm.
So can we do it for a overfit one, weak learner? Can we do it for a overfit, this technique?
The boosting.
Yes.
Mm, I think it should be doable. Uh, I think it should be done. I think we can perform both underfit and overfit model using boosting.
But in that case, all the H's are performing well, right? So
Um, the
the gamma will
gamma
be,
will be quite high. I mean,
yes. So
then
T
the
will
number of
decrease.
iteration, yeah, that will decrease.
Okay.
Hmm. Okay.
But T will decrease. But for each iteration, we have to go to the depth, means
Uh,
the time
that will
spent
be
on the.
very expensive, no? Yeah.
No, T will decrease, so it will decrease the number of iterations that we have to do.
But for
For each
every
iteration, the time required will be more.
time required will be more, yeah.
Okay. Because we
It
are going to the
usually it
depth
is
of the tree.
performed. Usually it is performed for the underfit model, the
Okay, okay.
AdaBoost, yeah. Okay, we'll stop here today. Um, so Sunday we'll meet next. Yeah. All right. Thank you, everyone. Good night.
Thank you.